So the key to quicksort is this idea of partitioning. So what exactly do we mean when we say partition? So let me write down an array, and I'll show you what the partition function should do with that array. I should say what a partition function should do with that array. So what is this idea of partition? I always leave off the last ti. Partition. So here's an array. Here's an input array to the partition function. So 5, 1, 3, 2, 4. So what the partition function does is it chooses a number, right? So it picks some number and then puts that number in a place in the array and rearranges all the other elements in the array such that everything less than that number is to its left and everything greater than that number is to its right. So the number it picks that it splits on is called the pivot. So first we choose, with lots of O's, we choose a pivot. Choose pivot. And I'll say to split on. And so suppose, for example, we chose 3 as our pivot. And there's no guarantee that what we choose happens to be in the middle. There's also no guarantee that what we choose happens to belong in the middle. But suppose we chose 3 to pivot. Then what the partition function would do is it would say, I'm going to put 3 where it belongs, and I'm going to make sure that everything less than 3 is to its left, and everything greater than 3 is to its right. So it might give me an output that looks something like this: 2, 1, 3, 4, 5. Right? This would be a valid output. Why is that? Because everything to the left of the pivot is smaller than it, and everything to the right of the pivot is larger than it. Right? So this is valid. Right? Here's another valid output for the partition function. Right? If it chooses 3 as a pivot, it could also give me, right? This is another option. Could also give me 1, 2, 3, 5, 4. Right? Where there's the pivot, everything to the left of the pivot is less than it. Everything to the right of the pivot is greater than it. Right? Notice that there's no guarantee that just because I'm to the right of the pivot that I'm sorted. Right? All I need is that if I'm to the right of the pivot, I'm greater, and if I'm to the left of the pivot, I'm smaller. Perhaps we get lucky and it is sorted, or perhaps it isn't. Right? There's no guarantee at all. Okay, so this is the idea of the pivot. Oh, and then the partition function returns the index where it left the pivot when it was done. So maybe it picked a number, moved it around a little bit, and then it wherever it left the pivot, it tells quicksort that's where I left the pivot, right? And so why is that important to quicksort? Because quicksort has to know what needs to be sorted still. All right. So there's a couple different ways of doing the partition. I'm going to introduce a version of it that was I think it was invented by the inventor of quicksort, and it's called the Hoare partition. Hoare partition. There we go again, leaving off the second ti. Partition. And so one of the things we have to be really careful about with these partition functions is not confusing the value of the pivot with its location. So the location of the pivot may actually change throughout the operation of the partition algorithm, but its value is going to be the same for one particular pass. Okay, so here's the way this works. Here's the way the Hoare partition works. Another one, by the way, you can also look up, and I think I'm spelling this right, you can look up the Lomuto partition, right? And quicksort is agnostic to your choice of partition algorithm. I'm using the Hoare partition just for historical reasons, but you could just as well look up the Lomuto partition. And if you ever have a quicksort algorithm that you're trying to use, a lot of times there's a flag in the algorithm that you can select, which partition method you want to use. And then there's other subtleties here too, which we'll talk about in a little bit here. But for now, let's just use the Hoare partition, and we're gonna do a very, very basic variant of it. So we have to choose a pivot somehow. So remember, a pivot is a number. It's not necessarily a fixed index. it could stay in the same index, but most likely it's going to be moving around, right? We have to allow it to move around. So we'll choose a pivot, and in this vanilla variant of the Hoare partition, we're going to choose this lazily. So we're just gonna be lazy, and we're going to pick the first element in the array as the pivot. So we'll be lazy, choose first element of array. Okay, and so if we look back up to our example here, it would have been totally valid for us to choose the first element in this initial array as the pivot. And so what we could have ended up with is, so there's our input array. If we had chosen the first element, this is what it would have looked like. So let me make sure I get these numbers right. 51324, 51324. If 5 were our pivot, then a valid output would just put 5 at the far end of the array and everything else to its left, right? So then what this could have given us is 1, 3, 2, 4, 5, right? This would have been a valid output. So that's an example where, if depending on how you choose the pivot, you may have to move the pivot around. In fact, the goal is to move the pivot to its final location, right? To the place in the array where it belongs. Okay, so we'll choose the pivot. In this case, we'll just be lazy. We'll choose the very first element in the array. So 2, we're going to start 2 counters. Start 2 counters, I and j. Start 2 counters. We're going to initialize I at the leftmost element, the leftmost index of our array. Well, not the left. I should say that we're going to initialize I just after the pivot. So this is just after pivot. Right, and so if we want to plug in a little bit of code snippets here, the pivot, P, equals A of L, right? Equals the leftmost element of our array. So initialize 2 counters, one of them at index L and one of them at index R, right? So I starts at the left, J starts at the far right. Okay. I will be incrementing. So each time the algorithm ticks, we're going to potentially increment I. And j will be decrementing, right? So I is walking this way, j is walking this way. Okay. So the picture is like this. We've got our array. The pivot is here. I starts here, j starts here. I is going this way, j is going that way. Okay, so here's how it goes. We increment I until we hit some condition. So until the place where until we find an element that's greater than or equal to the pivot. Increment I until the place where I is greater than or equal to the pivot. Okay? And then we pause. Okay, so I is gonna just tick forward until it finds something here. And so there's our AI. And the fact that I stopped means that AI is bigger than or equal to the pivot. Okay? And the fact that it got all the way there means that everything in here is less than or equal to the pivot. Right? So this is all less than or equal to the pivot. Okay? Then we'll decrement j until a very similar condition, but now it's going to be in reverse. So we're going to decrement j until j finds something that's less than or equal to the pivot. So until it finds something less than or equal to pivot, and then it's going to pause. All right, so here's our picture. J is decrementing, and suppose it stops right here. So here's a j. Okay, so what does that mean? That means that the fact it got that far tells us that everything here is greater than, is strictly greater than the pivot. Right, so these are all greater than the pivot. And in fact, I need to revise my earlier statement and say everything here is strictly less than the pivot. Okay, so what does that mean? That means that the pivot belongs somewhere in here. Okay, so now let's think about what happens after both counters have paused, right? We've interpreted this just a little bit, and now we see that we know that all that stuff that's before I is in some sense is where it belongs with respect to the partition. Everything that's above j is kind of where it belongs with respect to the partition. And so we just want to figure out what to do next. Okay, so now let me write a number 3 here. So once both counters have paused, we check to see if they have crossed each other. Okay, so first we can think about the scenario that I've drawn. So after I and j pause, now notice we haven't moved anything around yet. Everything is where it was when we began. So after I and j pause, we have case A that says if they haven't crossed yet, right? So if I is strictly less than j, so if I is less than j, then what do? Well, what do we have here? We've got this fact that aj is less than or equal to p, and ai is greater than or equal to p. Okay, potentially strictly greater than. So now we've got to decide kind of what to do next. So we've already established that everything to the left of I is less than the pivot, right? So it's small, right? So these things are all small, these things are all big, so they're fine. And we know that this is big, and we know that this is small, right? So what do? We swap them, right? We take the thing that's at location I and swap it with the thing that's at location j, right? So we swap ai with aj, okay? And what does that guarantee? That guarantees now that everything from I down is where it needs to be, right? Everything from I down is small, and everything from j up is large, okay? And that we haven't dealt with anything in between I and j. Okay, so now ai and down is small, right? This is after the swap, and aj and up is large. Okay, in the sense that small means less than the pivot and big means greater than the pivot. Okay, so there we go. So now we've swapped those, and now we restart the counters, right? So now restart I and j. So I can get I to continue incrementing and j to continue decrementing, and the same rule applies, right? You keep going until this condition or this condition are satisfied. All right, so now in case B, suppose that when they stopped running, right, when they weren't, or when they encountered things that were in the wrong spot, they had crossed each other. So suppose now that if I was greater than or equal to j, so either they were looking at the same element, or I went further up and j went further down, what does that tell us? All right, so what do we know in that case? Well, let's draw the picture. So we've got P here. We've got I started here and went up and up and up and up, and maybe we swapped stuff, but it kept going up, and it landed on a place right there. Okay, and J started here and it went down and down and down and down and landed on a place right here. Right, so that's where they stop somehow. So what does this mean? Well, we know now that, so if J stopped, what does that tell us? It tells us that it has something small in it. So J is small, and in fact, everything down here is small. And if I stopped, that means it found something large, right? So this is something large. And the fact that J made it as far as it did means that everything up here is large. Okay, so now what does this mean? This means that we have that everything between P and I is where it needs to be, and everything between I and the end is where it needs to be, right? It means that all of this is small, and all of this is large. Okay, and so now we just put P where it needs to go, and we're done. right? What does that mean? It means that we swap AJ, we swap the thing that's here, and P, okay? And the fact that, you know, AJ has been identified as small means that it's fine. It's fine to put it on the left of P, right? That's what it means for it to be small. So we swap these two. So if I is greater than or equal to J, we swap P and AJ, and then we return J, right? So part of the goal of this is to tell Quicksort, you know, where now is the partition, or where is the pivot, and so, you know, that tells Quicksort where it needs to do the rest of its sorting, and the pivot is now at index J, right? So we return J. Done. Okay, so in the next one, we're going to go through an example, but that's the Hoare partition algorithm. And I'm not going to go through the full pseudocode because I don't think it's particularly instructive. You can find it anywhere online, or you can find it in the Levitin book. But you know, my goal here is to give you an idea of how this works, and I think the next best thing to do is to actually walk through an example of Quicksort in action.